Hi everyone, welcome back to Mind and Maths. In this video, we are going to start exploring optimization but with inequality constraints. I'll explain what these problems look like and how we can use the Cohen-Tucker conditions to find optimal solutions. We'll go step by step through stationarity, feasibility, and complementary slackness, and then solve a complete question so you can see exactly how these conditions are applied in practice. Okay, suppose we have a generic format which is maximize an objective function subject to several constraints. Suppose I write it like this, that I want to maximize a function of x, and these are my three inequality constraints. Okay, so my first aim is to write down the Lagrange, I think. Lagrange, yeah. So the Lagrange function is going to be a function of x, and since we have three inequality constraints, therefore we will have three multipliers. I can call them lambda 1, lambda 2, lambda 3, and I want to maximize fx, and now I'm going to add in the inequality constraints. So I'm going to attach lambda 1 with the first constraint, and I'm going to write it as k1 minus g1x. So basically I want the following format. I want k1 minus g1x is greater than equals to 0. Similarly, I want the expression of the constraint for when it is greater than equals to 0. So I'm just going to fix this for the second one and the third one. Second one and the third one. So this is the second and this is the third. Okay. So then I have plus lambda 2 k2 minus g2x plus lambda 3 k3 minus g3x. So now let's start off by firstly writing down the KT conditions. So the first KT conditions. The first condition is that of stationarity. Stationarity means that if I take the derivative of L with respect to x, then I can put it equals to a 0. So that's the stationarity condition. The next condition is, to scroll down, it's called the primal feasibility condition, and these are basically just the constraints themselves. So in our question we had these. So these are my primal feasibility conditions. Yeah, so I have 3 of these. Next I'm going to have I think this is the third. Yeah, the third is the dual feasibility condition, which says that the value of these multipliers is either 0 or greater than 0. So they could be 0 or they could be greater than 0. The fourth condition is called complementary slackness. Complementary, MENTARY, slackness. And it goes like this, that lambda 1, which was the multiplier attached to the first constraint, we write it like this, that either wait a second, let me just write it down first. So the complementary slackness condition says that either there's one possibility that either lambda 1 is equals to 0 and this would be greater than 0, or the other way around. So this is what the once we do a question, you'll understand this part. Although I should write it here, there are two possibilities, that either the multiplier is equals to 0 and therefore the constraint can be non-zero, and the other possibility over here is that the multiplier is actually greater than 0, therefore the constraint is binding. Okay. Actually, maybe I should talk about this terminology as well. If we write g1x is less than equals to a k, this is called a non-binding constraint. So a constraint which is non-binding, and when I write this with an equality, then it's called a binding constraint. So if we think about this in terms of the budget constraint, it would mean that a person is consuming all of his income. So his expenditure equals his income. In a non-binding constraint, it would mean that his expenditure is less than his income, so there is room for saving. Anyhow, we will have in this question 3 complementary slackness conditions, because we have 3 multipliers and 3 constraints. Okay, so now we're done writing the conditions, so we can solve by we can start doing a question. But before basically I solve a question, there's a tip that I would like to share, that we have because we have 3 multipliers, therefore we have I think it makes 8 cases to inspect, right? Because each multiplier has 2 possibilities. So the first multiplier has 2 possibilities, second multiplier has 2 possibilities, and the third multiplier has 2 possibilities. So therefore we have 8 cases that we need to inspect. So what are they? Lambda 1 can either be greater than 0, or it could be actually equals to a 0. Same goes for lambda 2. It also has 2 possibilities, and same applies to lambda 3. So we have I think I'm going to just kind of extend it here so we have space. Yeah, this looks better, so the visual will be better. Yeah, here, over here, and then we have a possibility here, and then we have this possibility here. Okay, I think I'll just tidy this up later so I don't make the lecture too long. Okay, so what are the possibilities? Lambda 2 greater than 0, lambda 2 is equals to a 0, lambda 3 is equals to a 0, lambda 3 greater than 0, lambda 3 is equals to a 0, lambda 3 is greater than 0. Over here again we have lambda 2 is equals to 0, lambda 2 greater than 0, lambda 3 is equals to a 0, lambda 3 is greater than 0, lambda 3 is equals to a 0, and lambda 3 is greater than 0. So we have 8 possibilities, and we have to basically analyze each one of them and see which one gives us a valid solution in which all the KT conditions are basically verified, like they're not violated. So we'll have to analyze each and every one of these possibilities. So I know this sounds a bit overwhelming, but it won't. Once we do a question, then it won't be that bad. So I'm just going to do one question, and if this topic is still unclear, I can make another video and we can solve another question. For now, I'm just going to solve one question because I want just a short 30-minute video. So let's maximize utility, where we have a Cobb-Douglas utility function x into y, and I want to solve it subject to a constraint. So let's suppose that the price of x and is 1 and price of y is equals to 1. So let's assume price of good x is equals to 1 and price of good y is equals to 1, and income of this person is 100 units in whatever currency. So the first constraint is that the expenditure should be less than income. So px plus x plus py plus y should be less than equals to the income. So this is the first constraint. The second constraint is that x needs to be greater than equals to 0, and suppose the third constraint which is given is that y should be greater than equals to 0, and suppose the fourth one that they've given is that x should be less than equals to a 40. So remember, these constraints are provided in the question. I'm not making them these up. So these will be given in the question, and obviously for every question you're going to get a different set of constraints. Okay, so step 1, let's first make the Lagrange. Okay, so L is going to be a function of x, y, but now we'll have 4 lambdas. So we can say lambda 1, lambda 2, lambda 3, lambda 4, and then we have the function which is utility function xy plus lambda 1 is going to get with the first constraint multiplied with the first constraint, so we have 100 minus x minus a y. Then for the second, I have a lambda 2 into x plus lambda 3 into y plus a lambda 4 into a 40 minus an x, so a 40 minus an x. Okay, there's a bit of a there's something we can actually there's a way I can actually simplify this, which is kind of like, I don't know, maybe it's cheating, I don't know. I know that when we have we all know actually that when we have a Cobb-Douglas function, so the utility function actually looks like this and the budget line looks like this. So I know that I'm never going to get a point where either x is equals to 0 or y is equals to 0. That only happens when you have perfect substitutes utility function. So what I can do is, even though they've given me the question in this format, giving me so many multipliers, so therefore how many cases would I have to inspect? 2 power 4, which is for 16 cases. That's too much. So what I'm going to do is I'm going to change the question by saying that since we have a Cobb-Douglas utility function, it's not possible to have like edge solutions on the edge. So x has to be greater than 0. So therefore the lambda attached to it, which was lambda 2, will be is equals to 0. and y has to be greater than 0 and therefore lambda 3 is going to be is equals to 0. So basically my tip would be you should actually look at the functional form of the utility function before you construct the Lagrange. Oh, I don't know how to pronounce this. Is it a French word? What is it? I don't know. I'm Pindu when it comes to this. Okay. So I'm going to rewrite this. So I'm going to say we have L dependent on x, y, but now we only have two constraints. I can say lambda 1, lambda 2, and this is our utility function, and I'm just going to keep these. So I'm going to keep this one, and I'm going to keep this one. So I'm going to attach lambda 1 to this one and lambda 2 to this one. Okay, moving forward, I want to speed up. Lambda 1 will be equals to 100 minus x minus y plus lambda 2 40 minus x. So let's start writing down the KT conditions. First, we have to take the optimality condition, which would be the derivative of L with respect to x should be is equals to 0, and the partial derivative of L with respect to y should be equals to 0. Okay, so we have y minus lambda 1 is equals to and minus lambda 2 is equals to a 0. So that's the derivative with respect to x. With respect to y, we have a x here minus lambda 1 here, and there's no y over here, so there's no derivative there, so is equals to a 0. So this is my equation 1, this is my equation 2, and then the complementary slackness conditions, which are these two. So let's write these down. The complementary slackness condition, this is greater than equals to 0, greater than equals to 0. So this gives me two possibilities. We have lambda 1 greater than equals to 0, or 100 minus x minus y greater than equals to 0. Over here we have lambda 2 greater than equals to 0, or a 40 minus x greater than equals to 0. Okay, so let's start. We have actually I'll write this as 3 and 4. 3 and 4. What are the possibilities? We have 2 multipliers, so therefore we have 4 possibilities. So the first possibility is I don't need to make a T diagram. If anybody wants to do that, you can, but we have 4 cases to consider, and they are: the first would be if lambda 1 is greater than 0 and lambda 2 is greater than 0. The next that we need to see is that if lambda 1 is greater than 0 but lambda 2 is equals to a 0, then we have a possibility of lambda 1 is equals to a 0 but lambda 2 is greater than 0. And the final possibility is that lambda 1 is equals to a 0 while lambda 2 is also equals to a 0. So let's see which of these cases give us actually a valid solution. So let's start off with this case. So I'll just write this case 1, and I'm saying lambda 1 is greater than 0 and lambda 2 is greater than 0. Okay, so let's start off by writing my equations again. These were my equations. Okay, and according to the complementary slackness conditions, if lambda 1 is greater than 0, then what I'm claiming is that x plus y will be equals to 100. Otherwise, I'm not going to get a 0. Oh, there was actually complementary slackness means is equals to a 0 is equals to a 0. So if the multiplier is strictly greater than 0, then I need this to be equals to 0 to get a 0 in the end. Okay, so I have this one possible, and if lambda 2 is greater than 0, then I will have to have a x is equals to a 40. Okay, so let's write down. So if x is equals to a 40, then a 40 plus y will be equals to 100. Therefore, a y will be equals to a 60. And since lambda 1 is equals to an x, value of the first multiplier is a 40. And since lambda 2 is equals to y minus lambda 1, where y is a 60 and lambda 1 is a 40, therefore lambda 2, the second multiplier, is a 20. So therefore I have the first valid solution. So I can write this as x star, y star, and lambda 1 star, lambda 2 star. I'll make another video about multipliers and why these are important, and also we'll talk about the envelope theorem. Anyhow, I'm just going to write down the solution here. The value of optimal x is 40, y is 60, 40, and 20. So we've evaluated the first case. Let's move on to the second one. This was the second case. Let's do this. Oh, what happened? Oh, it's okay, I'll need this as well. Let's write down this. Case 2 was where is it? Lambda 1 greater than 0, lambda 2 is equals to 0. Lambda 1 greater than 0, lambda 2 is equals to 0. This is my second case. If I put the value of lambda 2 is equals to 0, from this equation, from the upper equation, I'm going to get y is equals to a lambda 1. From this I have an x is equals to a lambda 1. Therefore both of these combined give me a y is equals to an x. Okay, looking at the complementary slackness conditions, which were these, I'll copy them down so you can see what the case says. If lambda 1 is greater than 0, so if lambda 1 is strictly greater than 0, the only way we can get 0 is if 100 minus x minus y is equals to 0. And if lambda 2 is equals to 0, if lambda 2 is equals to 0, then we have a 40 minus x is greater than 0. Okay, so what information do we have? We have this information which we need to put over here, and we have to make sure it verifies this. There shouldn't be any contradiction. So I'm putting x is equals to y in x plus y is equals to 100. I'll have 2x is equals to 100, so therefore x is equals to 50, and y is also then equals to 50. And the constraint says that x will be less than 40. Again, this is we have a contradiction here. So the problem with a solution like this is that it's an invalid solution because one of the conditions is not satisfied. Okay, so for instance, if I write the solution like this, x star and y star, lambda 1 star and lambda 2 star, and I write it as this being 50 and then a 50 and then a 50 and then a 0, this is incorrect. The reason being is that this constraint is not being met. Okay, so a solution like this is invalid since x being less than 40 is not satisfied. I hope this scenario is clear. Okay, we have two more cases. Lambda is equals to 0, these two cases. Okay, let's just do them side by side. I'll just make, usually our answers are kind of compact. I'm solving this for the first time myself, so I'm not sure if this is gonna give the right answer or not. So this is my case 3 that I need to evaluate. This is my case 4 that I need to evaluate. And let's plug in the information. So the first equation, these were the first two equations. And then the complementary slackness conditions. So let's see, the optimality conditions become, this will become lambda 2 is equals to a y, and this will become x is equals to lambda 1, which is equals to a 0. So x star comes out as 0, which we actually said is not a it's not a valid solution. So I don't need to like solve it further, but let's just for our own satisfaction still solve it, which is like, let's just see if there's any kind of contradiction that we arrive onto from the complementary slackness conditions. So if lambda 1 is equals to a 0, it would mean x plus y needs to be less than 100. So y will be less than 100, since x is equals to, since x is equals to 0, this means that y should be less than 100. And the next constraint is that we had lambda 2 greater than 0. So if lambda 2 is greater than 0, this means that x has to be less than 40. X was equals to a 0, which is less than 40, so that's not a problem. The problem is that we don't know the value of y. Value of y is not known. And the other problem is that this never happens. Like, this is invalid for a Cobb-Douglas utility function. So basically, the case 3 is an invalid solution because we don't get corner solutions for Cobb-Douglas. And let's see case 4, when lambda 1 and lambda 2 are both equals to a 0. Then we have a y is equals to a 0. And this would give me a x is equals to a 0, which again is not possible because we can never get an optimal bundle here. It's not a possibility. So this is an invalid solution as well. This is an invalid solution. So there you have it. We've solved the one question, and I can actually make videos where we can solve more questions, because we have 3 types of utility functions, which are we can solve this whole thing for perfect substitutes and perfect complements as well. And obviously we can use this for profit maximization, and we can also use this technique for revenue maximization, or actually minimization of expenditure. So we can use this technique for several types of questions. Anyhow, I think this is enough for now. As recap, this is how we solve an optimization problem with several inequality constraints using the KT framework, once you understand how each condition links together from feasibility to complementary slackness, the structure of these problems becomes very intuitive. If you guys want, in the next video we can take on a few variations to strengthen your understanding even more. If not, then this will be the last video on optimization. Anyhow, take care, have a nice day.